Excellent. Very good. Welcome back, everybody. So we resume from previous lecture. So today we'll go through a quick summary of what we achieved yesterday and some more considerations on how to perform exploration in a reasonable, effective way. Mostly focusing on bandits as our test bed example. And then in the second part, we move to back to the full reinforcement learning problem. And we will just discuss a few kind of algorithms that can be adopted to learn without a model how to control an MDP. Okay. So, but first things first, let's go back to our summary of results. So starting out from yesterday. So what we have seen is that we can implement the general idea of control in absence of a model by basically setting up an algorithm which works as follows. So it's a loop by which we start out with some estimate for our Q function. Okay, so at the beginning it could be just a blank slate, all values set to 0 or all values set to random. Of course, the point where you start from has definitely a lot of importance in terms of performance, in the sense that the closer you are to the optimal solution, the quicker will your learning be. But you start from some guess anyway, which might or might not encode your prior knowledge about the system. And the first and most important thing is that starting from that knowledge, you derive some policy. Okay, so this is a policy which is derived from your estimate of the Q function. And here there are several choices, and we will discuss some of them today. The main and most important idea is that if you had perfect knowledge of the optimal value function, you would choose the policy greedily. Okay, so you would pick out the action which maximizes your expected return. But the point is that this is just an estimate, so you're not allowed to do that. If you do this, you fall into traps. Okay, so your experience might lead you to believe that you are choosing the best action, but this is not in fact the case. And if you just go full throttle for the option that seems to be the best, you may neglect other options that might turn out to be better, but if you don't visit them, you will never know. Okay, so this suggests that this way of turning estimates of the Q function into policy at each time step must carefully balance exploration and exploitation. So balancing exploitation. Yeah, exploration. And there will be more on that soon. Once we have a policy, okay, then we can sample our system. So we can observe, we can produce an action. And as a result of this action, we observe rewards and possibly new states more in general. If it's a bandit problem, you just observe rewards, okay, because states don't matter. But in general, you also observe a new state. And given these observations, okay, so this is select an action. And this is observe. And then from this, you construct your notion of temporal difference error. Which is a measure of the difference in what you have observed and what you would have expected based on your initial estimate here. Okay, so given all the steps that you've done before, given the estimate, you may also use the policy, etc. All these things together can lead you then to compute the temporal difference error, and then you use the temporal difference error to update your estimate. And you could do that by using some kind of eligibility trace. So this is the part which involves some credit assignment. That is, you have to give credit or blame the states and actions that you think are responsible for this discrepancy between what you observe and what you predicted that is encoded in the value of the temporal difference error. And in the most simplest situation, you solve this very simple credit assignment problem in the simplest of ways. That is, you give credit to the states and actions that you've just visited. So just what has happened in the very, very recent past. But of course, as you've seen, you can do better. And how better, this depends on the detailed properties of the underlying environment. So it's not easy to understand a priori in general. All right. Very good. So that's the general plan. And then we that's the general scheme of the algorithm that we will be playing. So this loop goes on and on with time, and assuming that you appropriately reduce the learning rate in this step. Okay, so this is in this step you perform your learning, and in this step this is where learning takes place. And in this other step here, this is where your updating takes place, or this is where the exploration. So you have to carefully reduce your learning rate and reduce your exploration rate so that eventually your cycling converges to the choice in which your temporal difference learning converges to the actual value of the policy, and the policy converges to the greedy policy for the optimal value. Okay, so you have to sort of guide your system slowly to converge towards this point. Okay, so that's it. We've been looking in detail into what happens if you are working with a bandit. So this is a recap. Bandits, which is the simplest situation in which you don't have any states. So we've been seeing that learning the Q of a given policy is actually a very straightforward process, which basically amounts to if you have a fixed alpha, so if alpha is constant, then your algorithm simply computes some recency weighted average of your rewards. Okay, for one for each arm, right? So remember that the algorithm here reads just like this. So your new estimate is your previous one. And then here there is the difference between the obtained reward and the previous estimate as well. Okay, so this is a sort of correcting algorithm, which amounts to say that you are doing some geometrically and recency weighted average. Okay, so in particular, if you choose this alpha to be dependent on the arm you choose and going just like 1 over the number of times that you've chosen that arm so far plus 1, then we've seen that in this case your estimates actually are nothing but the empirical averages for each arm. Okay. So in this very simple case, doing temporal difference learning coincides with just keeping count of the empirical average for each action you take. Okay, so you pull arm 1 and then you take a record. Okay, I've been pulling arm 1, say n1 times up to time t, and I've collected a certain number of rewards. Then I take the empirical average. I sum over all the rewards that I've collected for that arm. I divide by the number of times that I visited that arm, and this is exactly my estimate for the value function of that arm. Okay, and you do this in parallel for all the arms you play. Okay, then like I told you earlier, the greedy strategy based on this estimate fails. Okay, so this is what we've seen operationally, that there are regions in the space of estimated values in which you get trapped and you never learn the value of the optimal policy, and therefore you cannot get to the optimal decision-making solution. So summarizing, this is failure of greedy optimization. Okay, so greedy optimization means that you pick at every step your policy that derived from Q is argmax over A of your current estimate. This is the greedy option. Okay. So this is not working. And then we just discussed without any specific proof, but with just a sort of geometrical intuition, that one way out for this is to introduce some exploration. Okay, so there are different ways of doing that, and we will review some of them. But the basic message is that exploration is needed, is actually backed up by a theorem that is a result by Lai and Robbins, who provide a bound which says that so whichever policy, so whichever strategy used, that is good, okay, which has a technical meaning, but in short means that asymptotically you always choose the right arm, but only asymptotically. Okay, so you approach at the best possible rate the right arm. Every strategy that is good must choose suboptimal options at least with frequency 1 over time. Okay, which means that the cumulative number of bad choices must go like the logarithm of time. So this 1 over t is, if you think about it, is a relatively slow way of giving away exploration. Okay, so of reducing exploration. But if you do it faster than that, basically, you are certain to be confronted with some situations. There will be some situations in which the sequence of events will lead you to believe that your suboptimal arm is actually the best one, and therefore, from that moment on, you will stick to that arm. Okay. So if you are not allowed to go any faster than 1 over t in your reducing exploration, in your attempt at reducing exploration. And if you go any slower than that, then there is another price to pay, is that you are increasing your regret, in the sense that you are playing your suboptimal choices more frequently than you should. Of course, one caveat is that here there are prefactors. Okay, the prefactors in this are dependent on the properties of the system itself. So in particular, the precise statement of the Lyon-Robbins bound is that as the number of as time goes by and increases and approaches infinity, the expected number of times that you visit a suboptimal. Okay, so this is not the one where you have the largest mean, divided by the logarithm of time. This must be larger than 1 over the Kullback-Leibler divergence between the distribution of the suboptimal arm against the distribution of the optimal arm. And this tells you that if it's very important also the value of the constant here, right? So what is on the right-hand side, it's very important. So when you choose what constant to put in front of your exploration scheduling, here there is a constant, and this constant should be not too small either, okay? Because this constant should be compared with this Kullback-Leibler divergence, okay? So if you choose exactly this rate or going down like 1 over t, you should be also careful about the constant. And the constant is connected to some properties of your system which you don't know, okay? So this limiting value of logarithmic regret, logarithmic cumulative number of bad actions is, however, very fragile. So in practice, you should stay a little bit away from it, as close as possible, but not too close, because otherwise you may risk of falling on the other side of the boundary. Okay, so it's a sort of a fragile boundary to work on. Okay, so very good. So this means that there is some inherent statistical reason for which you cannot explore too little. Okay, it's not just that the algorithms aren't good enough. Any algorithm which performs well must explore enough, and this statement is made quantitative by this bound. All right, so one way of implementing exploration for real, okay, is, for instance, through epsilon grading. So examples of exploration. One, the epsilon gradient strategy makes a very simple choice. That is that every time the policy that you derive at time t from your Q is just given for each arm. Arm A is just given by the following choice. So it's either argmax. So let's write it more properly here, because this is not good. So pi t is given by, you pick the action AT, which is either the argmax of your QT, so I say t plus 1, which is either the argmax of your current vector of estimates. Okay, so for instance, you have all the sample means for the different arms, and you pick the arm with the largest sample mean, but you do that only with some probability 1 minus epsilon. Okay, so you reserve some quota of your probability for exploration, and then you do any arm, any action with probability epsilon. Okay, so what you do in practice is that you have your epsilon value, you extract a uniform random variable, and if this random variable is above epsilon, then you pick the maximum and you act greedily. But if it's below the maximum, you pick any action between the k actions that you have access to. Okay, so it's a very easy to implement. One obvious objection is that so these are remarks. So if epsilon is constant, exploration never fades. Okay, so this is not a good idea. So this is a clear no, because in this case, the number of times in which you choose suboptimal actions grows linearly with time. Okay? Because you always have a fixed probability, no matter how small it is, of picking something which is not optimal. So a better way to do it is to go and schedule epsilon. So I have some epsilon as a function of t, and according to the result that we had from Line Robbins, so one good idea would be just to choose it decreasing, like for instance 1 over t 1 plus some exponent, let's say unfortunately so many letters are taken that I don't know which one to choose, but let's say sigma. Okay, so with this sigma, which is something which is larger than 0. Okay, so you can make it as small as possible to get as close as possible to the limit, keeping in mind that if you choose exactly equal to 0, then you have to pay attention to the constant that you put here on top. So this is a reasonable choice, and in practice it works pretty well, except that it has one disadvantage in that it doesn't make much of a difference between different arms. Okay, so you explore with the same rate no matter which arm you're actually choosing. Okay, on the contrary, it would make more sense to select greedily the actions when you have visited them many times, and so you are comparatively more certain of the values that they have. And on the contrary, explore more the arms for which you have had less experience, and for them you expect to be less confident about the values that they have. So this suggests to use rates which depend on time, but also depend on the action you are currently picking. Okay, so let's think about this thing works. You have several actions available. Okay, you pick, for instance, one of them. You just select greedily one action, and then you choose how to explore. Okay, so there are two steps. You have your estimate. Okay, so you have your estimate. Then you have your greedy choice, which will give you a tentative action. Let's call it A tilde. And then you explore using this exploration rate. Okay, so if you happen to fall onto that your greedy choice sends you to an action that has been explored already a lot, then you do that, otherwise you don't. Okay, so this allows you to keep more balance between different choices. Then in this case, you do something very similar, that is you scale this like the number of visits for that arm to the power 1 plus. So the bottom line message is that there are several ways of doing exploration, even in the simple epsilon greedy model. And actually, when I write this kind of expressions like this, actually I'm hitting, I'm sweeping under the rug a lot of complexity in the choice, because you are actually choosing a functional form for this. Okay, so what is the power? But what is the function? Should it be something that goes down like a power law from the beginning, or maybe something which is flat and then goes down? Okay, there's a lot of craftsmanship in designing the way you explore. So all these things are hyperparameters for our learning. Okay, which sometimes need to be carefully tuned. Okay, so if you happen to have some practical experience with these algorithms, you might encounter the sort of feeling of dismay at the beginning, because, okay, but the algorithm was supposed to work and it's just supposed to converge, but in my hands, it's performing very poorly. In 99% of the cases is because this requires a lot of fiddling with these hyperparameters. Okay, so there is this, there's always this little distance between the beauty of the theory and the ugliness of the practice. So if you happen to work with these things, just think about it. Don't fiddle randomly with parameters. Think about what makes sense and what makes not, why your exploration isn't working, and what could be the issues that you're facing. Okay, so thinking a lot about how your hyperparameters should be adjusted saves you a lot of time in terms of convergence, practical convergence of your algorithm. Okay, but this was a little bit like a kitchen recipe. So let's move on, because I want to discuss before the break also other ways of doing exploration. So beyond, I'm reading. So one possible way of doing exploration is to smoothen out the operation of taking a maximum. Okay, let me break it down for you. But first and foremost, one thing that is not entirely satisfactory, even with this choice here, which is sort of the most refined one, even in this case, we are not completely happy, because we are not treating different suboptimal actions differently. So, but this, what do I mean? Suppose that you have 3 actions available, not just 2. So there will, one action would be the best one, and the other 2 would be suboptimal. So epsilon greedy, as we write in this here, is actually only considering the number of times that you have visited those actions, which of course, in turn, they depend implicitly on the values that they have. But maybe it's useful to make this dependence more explicit, or maybe not. Okay, so why don't we explore also independence on how suboptimal an action is more explicitly? So yes, it's important to know how many times you visited that. But if you visited many times and this action is abysmally low, maybe you should take that into account. Maybe it's not just out of bad luck that that particular action has a very, very poor estimate. So it's true that statistics is important, but maybe you're over-exploring even in this specific sense. So you could do something better. You could be a little bit more greedy, maybe. Okay. So one way of approaching these different ways of exploration goes like this. So I will sort of give you the basic conceptual steps. So let's restart over from. So greedy means that you are picking. Basically, what you're doing when you're doing greedy, you are taking the maximum over all possible policies for bandits of the sum over all actions for your current estimates. Okay. So this operation here amounts to picking up the action that has the largest Q. Okay, it's a simple linear maximization problem. You have a vector Q, which points somewhere, hat Q, your estimate. You have another vector, which is the vector of policies, which is positive, and it sums to 1, all the components. And therefore, the best thing that you can do is align your vector in the direction of the largest component. Okay, so this is absolutely equivalent to taking the argmax. It's just exactly the same thing, as you can easily check. How can we soften this requirement? Okay, so one possibility would be to do what is called an entropic regularization. So we replace the greedy strategy with this other request. So we want to maximize our policies the same quantity, but now we add a bonus for probabilities which are not too focused on a single action. Okay, so this is constant, where this beta appears as an inverse, and beta is strictly larger than 0. And here we put the entropy of the policy, the Shannon entropy of the policy, which I recall you is defined as sum over all actions. Okay. So you might recall, if you had a little bit of information here, but Shannon entropy should be familiar to most of you, I think, that the entropy is always positive, non-negative at least. And it is 0 only if pi is deterministic, which means that only if pi is concentrated on a single action. And the maximum of this is the logarithm of the number of actions, k. Remember that k for us is the number of actions. So probably I've never used this k before, so let's forget about it. Let's put just the number of actions. Okay, and the entropy is maximal only when pi is uniform. Okay, so only when each action, so pi of A is equal to 1 over the number of actions. These are basic properties of the entropy. And clearly, if we put this term here, this is clearly an exploration bonus, okay? Because if you want to maximize the second term, the entropy, you want your probability to be as spread as possible. Whereas the first term tells you to concentrate as much as possible on the largest value of your Q vector. So here there is a trade-off, there is a balance between trying to maximize your value and trying to balance this with entropy. Okay. For those of you who have a background in physics, this is very much what happens when you balance energy and entropy in your free energy. Okay, so there's a connection with statistical physics as well. Doesn't matter. The bottom line of this is that if you perform this maximization, which is a very straightforward analytic procedure, you can actually find an explicit expression for your policy. And the policy that comes out is, let's call it pi with a subscript capital B, which will become clear in a second. Is just the exponential of beta times your estimate divided by normalization of this. So we're summing over all possible actions B. This one's from 1 to the total number of actions. Okay. And this B stands for Boltzmann, because this is connected to the Boltzmann distribution in statistical physics, which is the same thing except for a minus sign, because in physics you minimize energies, and in machine learning and reinforcement learning you maximize rewards, returns. Okay, but apart from that, that's why it's called Boltzmann, and this choice is also called Boltzmann Exploration. So again, you might think of this beta as sort of an inverse temperature, okay? So if your system wants to align with a certain vector, but then you have some sort of noise in the form of a temperature, an effective temperature, which makes it wander a little bit around, okay? So it's a sort of physical, very, very loose interpretation of what this beta parameter means. More seriously, it's a trade-off between these competing requirements of being focused on exploitation. Okay, this is a way to make explicit the balance between exploitation and exploration. Beware, there's nothing fundamental in this, okay? It's just one intuitive way of writing down this balance, but there's no underlying law of nature by which this should be the right way to go. It's one among many. And as a matter of fact, even though this approach is widely used, it's unsatisfactory under many respects, okay? So the first thing is that, okay, let's go one step at a time. First of all, clearly, if beta is constant, you're not going very far from the viewpoint of exploration, because there will always be exploration, okay? So similarly as for epsilon constant, this is not a solution of your exploration problem, because you will keep on exploring. You will be exploring in a way that is different from different arms, okay, at variance with the situation with epsilon greedy, which randomizes blindly. Here you do this selectively, okay, because your policy depends on your current estimates. So you explore less than what you do with constant epsilon greedy, especially for the very suboptimal arms. But you keep on exploring, okay. So beta constant, as always, not enough. So what if we do the scheduling of this inverse temperature? Okay, then it requires a little bit of calculations, but you get to the rather intuitive results that your temperatures should grow sorry, your inverse temperatures should grow as the logarithm of time. Remember, if you want to go to the maximum, okay, here there is a way. If you send beta to infinity as a parameter, then this becomes the argmax. Okay, so it's obvious from this, because when beta tends to infinity, this second part disappears and you're back to the argmax. But it's also obvious when you look at the solution, because if you send beta to infinity, there will be just one term that dominates here in this sum. And the term which dominates is the one with the largest estimate, hat Q. Okay. So beta tends into infinity means that the temperature is going to 0 if you wish. Okay, so in a sense here you are cooling down your system very slowly, which is a procedure that is known in physics and in statistical physics as annealing. It's something you actually do with materials when you cool them down very slowly in order to prevent them to become amorphous. Okay, so if you have a mixture of materials and then you cool them down too rapidly, they might separate, they might become stuff. So when you produce some materials and you want to have them very homogeneous, you have to maybe to heat them up in order to make your mixture, and then you have to cool them down very slowly in order to prevent separation. And this is something which is, again, very loosely similar to this. And this logarithm of t is something which also you can derive by arguments from statistical physics, in case you're familiar with that. If you're not, doesn't really matter. This log t is the corresponding choice of 1 over t for the epsilon greedy algorithm, if you wish. Okay, now again we are going over. This is also not a good choice, because this beta parameter doesn't know which actions are visited more or less. So we are still exploring in a way that does not care about the uncertainty of the estimates. So we have to put into this estimate something that takes care of actions. And the way you do it is just now you introduce something which are temperatures for each arm. Notice that this breaks down the connection with entropy, okay, like we did before. So we are departing from that because the entropy requires here all beta to be the same. Now, so now we're making a leap and we're saying, okay, let's improve on this by introducing some action-dependent temperature, so to speak. And then one can find out what is the best way of choosing, or the one that gives you some theoretical guarantees on how to choose that. So I'm not giving you all the details, but I'm pointing you to a very useful paper, which is called Boltzmann Exploration, done right. And the authors are Cesa Bianchi, and you can easily find it out in the preprint repositories. It's a NIPS paper, I guess. Yes, NIPS 2017. Okay. So one thing that is interesting in this approach, so is that if you just regardless of the way you choose these parameters, this is suggesting that you should choose your arms according to your estimates by some choice like this. It's normalized. Which you can see as a sort of a tweaked softmax choice. One interesting thing, which is a mathematical result, is that actually you can turn this softmax into a sharp max by a trick. Okay, this trick, which I'm telling you, it doesn't require a lot of mathematical knowledge, but it's called the Gumbel Trick. Tells you that the actions that you pick according to this distribution above here, okay, is the same as picking the argmax over actions of your sequence of beta T A Q T A plus some GA, and this GA are independent Gumbel random variables. So you might not know, but a Gumbel variable, okay, so the probability density F for a Gumbel variable G is exponential, exactly, exponential of minus G minus e to the minus G. Let me check if I have not. That's correct. Okay. So it's a weird probability distribution. However, it has a very simple, nice form, something like this. Okay, centered around 0. Okay. So the nice thing is not about the Gumbel variable, which is interesting in itself because it's related to extreme value distributions. But apart from that, the interesting point here is that you can turn, using this trick, your problem of exploration by using some distribution, so by softening the maximum, like you did here, into a sharp maximum, but now you have to put your exploration bonus here. So here, what I want you to take home is that you can do two different things. Either you choose to the argmax and then soften it before, or you modify your estimates, because here you are modifying your estimates in a way, and then you do a sharp argmax on your problem. Why am I insisting on this? Because this kind of approach in which you modify your estimates connects with a class of algorithm which are called upper confidence bound algorithms. Which basically express the following idea. So, in short, you have your current estimates for your actions, and you must add some bonus for each of the actions So these are basically your empirical averages. And here you add some bonus, which takes the form, in particular for this algorithm, like under certain conditions like this. Okay. And then you take the argmax. Okay. So you construct your vector of estimates, which are your empirical averages here. You add some bonus, either random or non-random, doesn't matter. And this bonus means tends to promote the choice of these actions that you have visited the least. So if you adopt this correction with this exploration bonus, then your UCB algorithms are provably near optimal, in the sense that they come very close within the Lie-Robbins bound. Okay. So this is important, just as a side note, to say that there are very many ways of mixing in exploration together with your greedy policy, but they fall into two big classes. One big class is just to perturb your estimates, which is the second one, and the other one is to soften your argmax. Okay, fine. Now I think we've made a tour of many different choices. So if you happen to encounter them in the literature, they should somehow be not completely obscure to you. And this is definitely a good point to stop. And in the second half, we will go back to our original program, that is to use this exploration enhanced learning to achieve optimal control of an MDP without a model. Okay. Any questions so far? No, you look exhausted. Maybe
Can I make a question?
Yes, please.
I didn't understand what is the link between the entropic regularization and the Boltzmann exploration. Are they the same thing, or
This one.
are they? Yes, this one and the previous.
Yes, this is they are exactly the same thing as you say, in the sense that the result of this optimization, the solution, is this. You can work out the calculation if you write down explicitly this form, and then you take the derivatives and you maximize over the policies, respecting the fact that they have to be normalized. So if you do this simple exercise of finding the maximum over the policies, that's the result you get. So they are the same thing.
Okay, thanks.
Sure. Any other question? Okay, so let's take a break and we reconvene at say 10 past 10, okay? See you later. All right. So now we are ready to discuss in general the algorithms for reinforcement learning in model-free case. And in order to do this, yeah. So we want to, like I said, we want to control our system in general for a generic Markov decision process. So what we're going to do now, we're going to write a sort of master code, and then we will see how we can implement the various modules of this master code in different ways, master algorithm in different ways, depending on choices that we might want to do and what are the differences and advantages. Okay, the basic structure of our algorithm works like this. So initially, you have to initialize your parameters. Okay, so you define the state of space, you define your learning rates, initial learning rates, or your initial exploration rates. Okay, it's a sort of general procedure. And then you initialize your estimate of the Q function. Okay, so this is an estimate. So it should have a hat on top of it, but let's not add it in order to not to overburden the notation. So this is your initial guess for the Q function. Okay, and then you have a loop that starts here, which does the following. You may want to. So this is another possibility. You may want to break your learning into episodes. Okay, so you may want to run your update for some time and then restart again somewhere. So this is one possibility. In order to account for this possibility of having multiple restarts, which is pretty natural if you have a goal task. So your episode ends and then you restart it. But even if it doesn't end, at some time you say, okay, maybe I stop here because my value function is not increasing any longer, so I restart. So in order to include this this possibility, we can have a loop over episodes. And at the start of every episode, we have to start from somewhere. Okay, so the first thing we do, we initialize a state. Okay, so we pick up a state according to some initial distribution that we choose, which should be uniform enough in order to allow the system to visit different states. Once we have that, we derive a policy pi from Q. So what does that mean? For instance, this is the part where we have to use to balance exploitation and exploration. So for instance, with some epsilon greedy or softmax or your favorite choice of exploration. Okay. Once you have that, you can choose an action A according to your policy pi. And now you take action A and you observe the reward and the new state. So once you have that, now here enters two submodules, if you wish. So the first one is compute the temporal difference error, delta. And the second one is compute the eligibility trace E. This is a matrix. E is a matrix because it has eligibilities for states and for actions here, since we are working with state action values. So we will make everything explicit in the following, but here these are two functions, if you wish, which can have different content depending on the specific algorithm. So these two parts are algorithm dependent. And today we will mostly discuss what to do about the temporal difference error. And we will keep the eligibility simple, but you can combine the two. These are basically two different independent ways of combining things. You can have eligibility traces, which could be TD lambda or whatever. There are several variations on the theme. It's a very rich field in itself. It's very well covered by the book of Sutton and Bartow, as well as this part, of course, but for in the interest of time, we will specifically focus on the part of computing the temporal difference error. Okay. Good. Then once this is done, we update our Q matrix. Okay, so this is often used the symbol to mean that we are updating. So our new Q comes from the old Q plus some learning rate, which can be dependent on time, on action, etc. Let me use this symbolically. Times the temporal difference error, which is a scalar, it's a number, it's a real number, times the eligibility trace, which is in general a matrix. Okay, so this is a Q is a matrix, state action matrix. This is state action matrix. This is a real number. This is a real number, which depends, of course, on Q implicitly. And this is the eligibility trace, which depends on the past history of actions and states that are being visited. Fine. And then what we do basically is that we call our new state as the old state, and the loop. So this inner loop here, this is another loop. This inner loop here ends, okay? Because we have produced a new state and we can restart from the state that we have here at this stage, okay? So the loop, the inner loop basically is this one. Okay, so we have this one episode, and we may have many of them by refreshing our S at random and repeating this loop. Okay. So this pseudo algorithm, under appropriate choices of the functions that are algorithm dependent here, which we will discuss in a second, and eligibility traces. So this part is, sorry. This part is algorithm dependent. Converges with probability 1 to the optimal solution of the Boltzmann's equation, given a proper scheduling of exploration and learning. Okay, so for the learning rates, you know how they should look like according to the sufficient conditions by Robbins and Morrow. And for the exploration rate, you know that you have to choose them carefully, and for epsilon greedy, a good choice would be basically close to the inverse number of times that you visited that state action pair. All right, good. So, so in this sort of super algorithm, we can then specify different choices for our computation of the temporal difference error. Okay. So, and also for the eligibility traces, but let me put here a little break and say in the following. We just focus on the eligibility trace of a certain state and action. It's just going to be 1 for the state that I've just visited and for the action that I've just taken. Okay, so this is the simplest choice of eligibility traces, which corresponds to the algorithm TD node, which means that all the errors that I'm observing are to be credited to the last state action pair-derived visited. So there is only one entry of my Q matrix here that changes at each time. And it's the entry which corresponds to the state action pair that I've just visited. This is, of course, a limitation, but it allows us to write down, to focus on the interesting part, which is how to compute the temporal difference error, which is this part here. On the book by Sutton and Barto, you see all these things combined in different flavors. Okay. So when it comes to how to compute different estimates for the temporal difference error, we will now review 3 possible situations which cover a lot of the work that has been done in the last 30 years, basically. And the first of these is called an algorithm which is called SARSA. SARSA is a quite trivial acronym for state action reward state action. Okay? Because the way in which the temporal difference error is constructed here requires the evaluation of an additional state and action with respect of an additional action with respect to the usual stream that we use for that. Let me be more explicit. So in SARSA, the recipe for the temporal difference error is the following one. It's just the reward plus gamma, my current estimate at the new state and the new action minus QSA. Okay, so this is closely resemblant of the recursion formula for the Q value. Okay, you remember that you have to average, the average of this delta is exactly the recursion relationship. Okay, so this is a very natural choice from the viewpoint of stochastic approximation. You will notice that one key aspect is that you have to choose in advance your action A prime that you will use in the following. Okay, so this requires a double extraction of actions, which are the 2 A's in SARSA. So how do you pick that action? Well, you use always the policy derived from Q. Okay, so A prime is taken from the same policy derived from Q. So you use this policy twice in SARSA. You use it once when you choose the first action here, and you use it also in the belly of this function, inside this function, to compute a new action A prime according to the same policy that you are using at the moment, in order to construct your temporal difference error. And then you return. Okay? So this is one possible choice. Now we will see another possible choice, and we will highlight the similarities and the differences. The second choice is called Q-learning. And the temporal difference error in Q-learning is defined as follows. So you notice the subtle difference between these two in what is happening in defining what is the Q value that you are comparing against for the future, for the next step. Here you're taking the maximum of your Q function. So you're using a greedy choice just to evaluate the function, not for the policy. The policy still is epsilon greedy, but you're using this maximum to evaluate a term in the temporal difference error. This makes it more similar to what you have in the Boltzmann equation. Okay. So this is closer, SARSA is closer to the recursion equation. Q-learning is closer to the Boltzmann's equation, in that you take a maximum of your estimate. These have some advantages and some risks. The advantage is that this is more aggressive, okay, and you go closer to your best policy. But also being more aggressive, in a sense, explores less inside this choice, okay? Even though term exploration is a little bit of a misnomer here, but you sample less because you are not given the possibility of sampling this. Of course, if you sample here, you have more noise because you are sampling another random action. So this object here fluctuates because of choices in different A prime that you might have. This one doesn't. So the good thing is that both algorithms provably converge to the optimum. Okay, so if you schedule appropriately your learning rates and exploration rates, both of them converge, but their finite time performance could be very different. So before convergence, they might be doing very different things. Okay. So in Sutton and Bartow, there is an interesting example which is given, which discusses the difference between SARSA and Q-learning for finite time performance. And let's discuss it very quickly here. You can see all the details on the Sutton and Bartow books.
Excuse me.
Yeah.
Can I make a question before?
Yes,
just a small thing. What's the difference between, because I'm making confusion with the notation between the A uppercase prime and A lowercase prime?
Yeah, thank you. So the upper cases here are meant to be the states and actions that you observe or choose along your sequence. Whereas here, the lowercase means just that that's the index of the matrix, okay? So, right? Is it clear to anyone? This is just a formal operation over indices, the one that you have here. So you have your matrix, you just look at all the rows. You just look at the row with the S prime which you have just visited, and you look at all the columns and you pick the maximum. And all this S and A means that you are focusing only on that particular item in the list. Okay. So the example that Sutton and Bartow discuss is called cliff walking. Which in a nutshell, it's a grid world problem in which so your interest of going from a start point here to a goal point here, and here there is basically the edge of a cliff. Here is the cliff. So basically, if you step on the cliff, you get a very, very negative reward. So this region here, you get very negative rewards because this means that you're stepping off the cliff and you're crashing down and you will be badly hurt and it will take you a lot of time to recover, okay, in common words. At the same time, you get a penalty for every time you walk onto the ordinary part of the cliff, which is just the cost because time is going by. So the basic idea is that you want to go to the goal with the shortest path, which is something like this, because you want to get there in the shortest possible time. But you don't know that the cliff is there. You're basically it's a little bit like you're blindfolded and you don't see the cliff. At the beginning, you start out and you just have this map where you can sort of mark down the points that you have visited. Okay, the usual thing is model-free learning. You don't have a map of the system. You just have to learn by experience what is the best way to do. And so when you run SARSA on this algorithm, again, with fixed exploration rate, so we're talking about finite time performance of SARSA, not the asymptotic one, which is optimal for both. So typically SARSA, what it does, it just goes about like this and takes a safer path. Okay, so this is the safe path. Why does it do like this? Because there is this second action that is taken. So it looks one action ahead in the future. And if it steps on the cliff, it realizes that this is going to be very bad. So this motivates it to go through the safer path. On the other hand, Q-learning works much closer to the path, to the cliff. So Q-learning learns a policy which is closer to optimal, but the performance in terms of the reward is lower because it falls off the cliff much often, because there might be noise in the transition, etc. Okay, so you see that these two algorithms, even though they have the same asymptotic guarantees, when you just see how they work in practice, after a certain number of episodes, they may display different behaviors. And this uniquely depends on the only difference that there is, that is how you estimate your temporal difference error. If you estimate it using one kind of policy or another one. And this is the first remark. The second remark about the difference of these two is that SARSA, you see, always uses this policy pi, both for choosing actions and for estimating. Okay. Pi here, this new action here is estimated using the same policy. This is the same as in core algorithm. Q-learning uses a policy to choose actions, but uses greedy to estimate. Now, greedy, you can think of greedy just like another policy. So this is why usually we say that SARSA does on-policy estimation and Q-learning does off-policy estimation. So this is a degree of freedom which you can use, and sometimes is useful to use off-policy estimation. So you act according to a policy, but then you want to sample your future according to another policy which maybe works better. So in applications from computer science, it's absolutely legitimate. If you think about sort of the neural interpretation of reinforcement learning, that is how it works in our brains, in decision making in animals, it makes a little bit less sense because you cannot sort of disentangle these things that you are doing and sample in a different way. Okay, so it's less intuitive, but both things exist, and this distinction is very important because as we will see in next lecture, not tomorrow but the next week, when you combine these approaches with the function approximation, because now we're working in the tabular situation in which we work with states and actions which belong to Markov decision process. But the next step will be to use approximations in order to deal with vast state action spaces. And when we combine in conjunction temporal difference learning, function approximation, and off policy, then disaster can ensue. So off policy algorithms tend to have troubles when they are mixed in with the temporal difference methods and function approximation. Okay, nothing to be worried about at this stage, because this is something we'll discuss next time. But this is just to introduce already from now the notation of what is on policy and what is off policy. Okay, one more thing. We can have another choice, which is inspired from SARSA, which is the following one. Do we really need to take another sample according to the policy pi, or can we do something else? Maybe something smarter. And this possibility is what is called expected SARSA. So the idea is similar, but now we replace this random estimate here with the average with respect to the policy. Explicitly, in expected SARSA, the temporal difference error is the reward plus gamma. And here I'm putting sum over A, policy A as prime. Well, let me put A prime here. All right. Okay, so you see the difference is in this middle term here, which now is not a sample according to the policy, but it's already an average over the policy. So this is an operation that you can do because the policy is in your hands, is the object that you have derived from your Q. So maybe it's epsilon greedy. So you use this explicit expression to combine the entries of your Q matrix in a different way. The advantage is that you don't have fluctuations any longer now. So this is reducing your noise in the estimate of the temporal difference error. And in fact, when you check for the performance, so I'm not sure, but maybe tomorrow there will be also an example with expected SARSA. I hope so. You will see that the performance with respect to SARSA is increased. And this comes with no disadvantage because this still is on policy, because you're using always the same policy pi to estimate your temporal difference error. So there are less fluctuations. In delta, and still on policy. So, in fact, there is a sort of overarching scheme which combines expected SARSA and Q-learning, if you wish. So you can also view, so let's call it 2 bis. Another view on Q-learning. You can write down your delta as R plus gamma sum over A prime of some other policy pi tilde Now, look at this expression here that I just wrote down. It's just the same one that I have for expected SARSA, except that now I'm using another policy here. It's not the same policy that I derived from Q in the previous step. It's another one, could be anyone. And in particular, if pi tilde is the greedy policy from Q, so it's argmax of Q, then this thing is equivalent to Q learning. So by choosing your estimating, this is your estimation policy. If pi tilde is equal to pi, then you are on policy, and then everything is fine, and this is expected SARSA. But if your pi tilde is different, you have a continuum of choices which go from pi to the greedy choice, and the greedy choice corresponds to Q learning. Okay, so there is a full sequence of algorithms that you can choose which interpolate between expected SARSA and Q learning, between the on policy and the off policy. Okay. So all these three things are clearly related between each other, as they should be, because all these choices for the temporal difference error eventually must converge to the Boltzmann equation. So it's clear that they cannot be totally independent from one another. But this allows us to sort of have a view on very different algorithms that have been proposed and the relationships between them. Okay. So clearly this was just a quick overview of the most important algorithmic approaches to temporal difference learning. Each of those may have better performances depending on the case at hand, depending on the choice of the hyperparameters. So there's a whole set of competing algorithms that are slight variations on the theme. So we don't discuss them at all because this is not the purpose of this overall course. The purpose is to give you some general broad ideas from a high-level viewpoint. But if you happen to open up a paper on reinforcement learning, you should sort of be able that within this class of algorithms, which doesn't cover all the possible classes of algorithms, we will be discussing very different architecture in future lectures that connect to these ones, but only in part. But for this class of algorithms, the basic concepts are already laid out in this lecture. Okay. Very good. So I think we're done for today. Tomorrow we will have tutorials on these exercises, especially SARS and Q learning, and hopefully also expected SARS. With that, I'm done. And if there are any questions. Okay.
Sorry, can I make a question?
Please.
Can we say again what we mean when we talk about episodes?
Okay. So I didn't discuss this much, but let's consider, for instance, the problem of cliff walking. Okay. So how do you learn in this particular problem the optimal policy? So let's look at the original pseudocode. Sorry, too much here. So the first step is that you choose some initial state S, which in this case will be the starting state here. And then you start a loop, and you start with your guess Q function, which maybe it's flat, it's totally zeros. So you take some first step at random. Then you pick an action, you observe some reward because there will be some cost. Either you walk off the cliff or you stay out. And then you improve your queue, etc. And eventually, since the domain is finite, either by chance or not, either you walk on the cliff, I mean, you collect many penalties, but eventually you end up in goal, G. And when you're there, your episode finishes, okay? Because you have reached the target one way or another. And then you restart again from S, but keeping in memory all the experience that you have done in your cube matrix. So you restart over again with a new experience, but with the Q metrics that you have learned so far. And then you repeat this many times. And each of these stream of data, which brings you from the starting point to the goal point, is one episode. Is that any clearer?
Yes, and thanks.
Any other question? Okay. If not, have a nice day and see you tomorrow morning. Bye-bye.
Thank you. Goodbye.
Thank you.